So good morning, everyone, to our summer school again. Nice to have you here again for this session today. We will focus on the fiber-reinforced plastics and how we could model this with LS-DYNA and how we can use our software products to generate material cards. Okay, this week we had several topics and first of all, the content of today is I want just to have a short summary on yesterday. Then I would like to introduce to you the for a MicroMec and then look in material models in LS-DYNA that are available. What is the motivation on considering the fiber reinforcement in the simulation? What material models could we use and how we can use them? What is their manufacturing influence? And how we can characterize the material. And finally, I want to conclude with a case study to show what is the benefit. After that, we would like to give you an outlook to the composite. My colleague Harish will tell you about that. So the last days we were talking about our products and especially we were focusing on the topic thermoplastic materials and how to generate especially material cards with AutoFit and what tests are needed therefore. We've shown you how to make a material model with easy approach on bending for MAT24, for instance, or for viscoplasticity with for Mises yield surface. Yesterday we focused on more general yield surface, as you can see here in this slide, and we were showing you how this AutoFit could work. I just want to show you some additional information on that shortly. Often perhaps you will think about, yeah, they showed me the AutoFit and how could I start in a project with it? And therefore, let's have a short look in our software again. And if we do so, if we would start in our software with a new project by choosing here this folder icon, so you can see it here. And when we choose it, then we have a blank database. And if we want to make a material characterization, we just say, yes, I want to use a stored test plane. I'm choosing it. And here, please remember, we were telling you about the packages we have. In each package, you just have some standard tests in it. For instance, I choose the ISOP standard package and automatically the database is copied and a new database project will start up. As you see, everything is now in here, all tests that have to be conducted. They are just clean, you have just to test it, and they're already linked to all models and also already linked to the AutoFit procedure. So mainly if you have conducted all tests, you finally just choose the model in the model area and then say AutoFit. And so it's quite easy to make a material card from the blank from the crash. So it's and so that you have in a short way a standard material card. So this was now a short introduction, a short recap on the last days and how you could start with such projects. Now I want to focus on today's topic. And first of all, I want to talk a little bit more about MicroMec. Because we were talking the last days mainly about impetus and Valimat, and MicroMec for fiber reinforced materials is a key enabler. So this key enabler helps you to find easy ways to to make the material cards. We will see later on live. So, but to give you more information what is behind MicroMec, I would like to tell you a little bit about the history of MicroMec. So first of all, MicroMec was a standalone product. So we developed MicroMec in the nearly 20 years ago. And MicroMec is based on the mean field theory. So typically in the mean field theory, so you make a mean field homogenization. In the background, you have the typical Eshelby tensor calculations, and we're using then an orientation averaging, and based on that, we then can finally calculate the composite properties. So by defining the properties of the matrix and the fiber, we can calculate the composite properties, and that can be stresses, strains, and so on. And here you can see a comparison which was conducted by University of Leoben between MicroMec and Digimat. Perhaps Digimat is well known for you. And as you can see, it's quite similar results for the same input. And yeah, it is mainly on the same theory. After that, we started to implement MicroMec as library into our software Valimat. So as a standalone product, you could use it and calculate the properties and use it, but we thought it is more convenient to implement it directly in our software. So for that, I would like to show you this directly in our software. So I switch back. I open a prepared database now, which I want to show you today. Okay, it's loading. Okay, good. So in that case, I just start from the scratch. So I make a new model. Press here this new button. And I call this model just explain MicroMec library. So it's okay. To explain the MicroMec library, I have to choose some kind of material model which includes. So I have to choose a material model which includes anisotropy. So for instance, I just say not selected here, everyone, and I'm choosing something what is not isotropic elastic. And then I get all LS-DYNA material models because I've chosen to solve LS-DYNA, but I could do this also, for instance, for different model, like I do Abacus here. Then I will get elastic with the engineering constants, for instance. And yeah, so now we have such such material model in here, and now we want to use the micromechanics. And yeah, to use that, we just have then to choose here MicroMec, and we have lots of opportunities to choose what type of composite we have. For instance, we could just say it's an endless fiber reinforced material, okay? And if I want to see what we would say we're using epoxy hearts, so I know for epoxy, for instance, we have a density of 1200, a Young's modulus of 3200, and I can choose then the fiber. For instance, I say I have a glass fiber here with a volume content of 50%. And as you see, automatically the micromechanics calculates you the properties here. So I see the density of the material, I see the Young's modulus, I get the shear modulus and the Poisson ratios. So if I say, yeah, I don't have 50%, in reality it has 53%. I just change it and automatically the values are calculated, and then I just validate my material model. So it's quite easy to use this micromechanic in our software directly. So you just have to define what setup I have. Do I have endless fiber? Do you have particles, short, long, fibers or fabrics? So for instance, we just want to switch to a short fiber. We are switching to a short fiber. And as you see, we get less data because, yeah, we get typical standard values in here. Okay, now we say we have 30 mass percent glass in it. And we can then also define the fiber orientation here and say, yeah, the orientation is 50% in the 0 direction, 40% in the second direction, and automatically the values, the elastic properties are calculated, and I can use that in the micromechanical approach. Okay, do you have any questions to that? So as we have MicroMec implemented this library, we can use this library to generate material cards. Over the years, we developed a user material for several solvers, and this user material developed in Fortran is based on this mean field theory. So we have a main framework, meaning that in this material model, we get the composite stresses and strains as a step. Then we can calculate what happens in the matrix. Based on this condition, we can then decide, yeah, we're going to a plasticity algorithm or not. And after that, we can go back and calculate the fiber stresses and go for failure and calculate the composite strains. So that's quite straightforward to use that as a user material. And I think it was 5-6 years ago, so we were talking with Dynamore, and so we together decided to use this user material and implement it in LS-DYNA. And since LS-DYNA version R10, you can use this user material as official material model, so-called MAT4A MicroMec. So now you have these opportunities also available in the solver. And as you see, we did lots of validations and verifications if the material model is working fine. So as you can see, we just simulated it. Always here you see the stiffness. Okay, I have not switched the presentation. Sorry. Okay, go back again here. So I was explaining how this is working in this implementation, and I was talking about that we have it implemented as user material, this mean field theory, mentioning that in this user material model we are coming from composite stresses and strains, can calculate the matrix stresses and strains, and finally can check if we get plasticity with the yield criteria. And we can then go further to get fiber stresses, damage, and give back again for the user material the composite stresses and strains. So that's straightforward. And as I mentioned, this is available as user material model in as standard material model in LS-DYNA. And these verifications we have conducted to see if everything is working fine. So we set up a big LS-opt file with a design of experiment and tested it in different ranges of matrix properties and fiber properties. And if I say I have a material model with 100% matrix and do a single one element test with an orientation, I will see over the orientation of this, clearly I should get the matrix value which I give in. And if I say 100%, I should get the value of the fiber as response. And if I do this, for instance, for 2 fibers and say 60% fiber in it, then I get this typical diagram that the stiffness will decrease over the orientation. So that was done in these verifications, and yeah, I already mentioned we did lots of robustness tests to see if this material model works quite fine. So what other material models are available in LS-DYNA? So in LS-DYNA, we have lots of material models available, and we can decide depending on which material we have. So we can say, yeah, on the one side we have this short and long fiber reinforced thermoplastic materials. So this thermoplastic materials typically have fibers in a length of 0.2 to 1 millimeter, so quite short. On the other side, we can have this typically high sophisticated composites, high strength composites or high stiffness composites with carbon, glass, or Kevlar, which could be used with endless fiber rovings or fabric, or used by such cold process with resin transfer molding and so on. And so we have different classes of models. On the one side, the classical composite models, what we have here, which mainly are based on an elastic domain, autotropic elastic domain, which have no plasticity in it. And typically, then you couple this elastic domain with some kind of damage to describe how the failure reduce the stiffness and the strength. This can then coupled with some kind of strain rate dependency, like in the beginning with viscoelasticity, or have this strain rate dependency on the strength, for instance. And we can also have some advanced composite failure criteria to mention. I think so is Tsai-Wu, which is quite famous, and also the criteria around Book, which are somehow the father of the Binyo and the Camanio criteria, which we can find. This is the one class. The other class is what we need is for the short and long fiber reinforced, thinking that in that case we have not so much fiber in it, typically just 10 volume% fibers in the material, and their plasticity plays a quite big role. And as we see, we can define in this material models plasticity. And I will talk later on. Yeah, lots of you are using isotropic approach because this plasticity is quite important for you. But there are also others like this MAT 157, which is has an anisotropic elastic behavior with an anisotropic Hill description for the plasticity and so on. And this is also a composite definition here. So you have to say what is the Young's modulus in one direction and another direction. So as I showed it with the library in Valimat. And a total new thing is this MAT for a MicroMec, because this is a micromechanical motivated model. So you directly can define the properties of the fiber and of the matrix and calculate the composite in LS-DYNA directly. So now let's talk a little bit more about short and long fiber reinforced materials. So if you conduct tests with a bending test, you will see, depending on the direction, if I'm doing a longitudinal, a diagonal, or perpendicular testing, I will see that I have a different material behavior. And typically, customers decide to make MAT 24 with some gizmo because they are familiar with that. And yeah, then there are different options, just averaging it, or just make a material cut on an orientation of samples which were cut out in 30° or 45°, or make one material cut for the longitudinal direction and make one material cut for the transversal direction, and look at the mean and maxima in your simulation. Yeah, that's quick and dirty, and is working from making the material cut quite straightforward. But if you look at this is current standard in the simulation, and if you look in the simulation of this sleeve, so this is a cable sleeve. We will see later on more on that. And this cable sleeve is tested in a drop test. As you can see, we have a drop tower and we have a wide, it's falling down, and the sleeve is failing here. So it breaks in this area. And yeah, if we use this isotropic approach, we get the wrong response of our simulation model. So as we have all the same behavior, we have the highest strengths here in this region, and clearly then it will fail here. So that's not the reality. And it doesn't matter if you use the green or the red curve, the weak one or the stiff one, you always will end up, because this is a geometry, influence at that point as the maximum or the critical point, because you're using an isotropic modeling approach. So let's have a look what is typical for this material class. So we have a back door which is injection molded, and we have several injection gates here. And if we do a mold filling simulation, in that case we did it with mold flow, we then get the fiber orientation. So as you can see, based on these injection locations, we get different fiber orientations locally. So red means highly orientated and highly oriented, and green and blue means not so oriented. And typically then you can calculate average fiber orientations that can be described with such kind of tensor. So meaning this is some kind of probability if you are searching in the location, in local location, and in the space, in the sphere, then you find 66% in the first direction, 32% in the second direction, and 2% in the thickness direction. So that would be some kind of average. If I look here in this region where the flow itself will go more into shear and will lead that the fibers are orientated like this brace is, then we find out all fibers are highly oriented, and yeah, this will then lead to a higher fiber orientation tensor. So in that case, 90% of the fibers are oriented in that direction. And as you can see, depending on how the part is filled, I have local different properties of my material. And yeah, as you know, this fiber orientation and how the fiber could support the matrix and stiff it, we will see if all fibers are in this direction for 30% long class fiber, we will be at the Young's modulus of 10,000. If we say we are transversal, no fiber, it's at the level of the matrix itself, a little bit more. And so with increasing fiber orientation, our stiffness will increase and our mechanical properties will also increase. So what is the typical material behavior? Let's look in a little bit more detail on it. So we conducted some bending tests to explain it. So this is data was provided by Celanese. And so first of all, if we look at different directions, so we cut it out bending samples in different directions. So we molded injection molded some plugs and cut it out samples in injection direction and transversal direction. That's the green one. And the blue one would be in 45-degree or diagonal direction to the injection flow. And as you can see, we conducted this all at the same conditions. Based on how you cut it out, it's stiffer if it's in flow direction, or it's weaker if we are in transversal to flow direction. If you do this for different materials, like having 30% fiber in it, mass percent fiber in it, 40, 50%, this fiber content will lead us to a stiffer response and also to an earlier failure behavior. So as we see, that's the influence of the fiber. If we conduct tests under different strain rates, meaning making static and dynamic tests, you see the blue curve here and the red curve here, that would be in longitudinal direction. You see, if I have a higher impact velocity, then it will lead also to a stiffer response. The same would happen in the same level for the transversal direction. And if I do tests for the same direction for different temperatures here, also dynamically, then I will see, yeah, this will lead us also to different behavior. As the temperature is decreasing, also my stiffness is going down, but I get more ductility. So that's the influence of the matrix. And we can see here, if I have a composite, then the composite response is dependent on the fiber and on the matrix. And matrix gives you the temperature dependency and the viscoplasticity, and the fiber gives you the reinforcement, meaning the value, the content, and the orientation itself will lead you to different behavior. So that should be kept in mind, because if you want to material model that, that's quite important then, to make it, because with that background information, it's then easier to make a material model. So now let's have a look again on the material models in LS-DYNA, and I divided it in different categories. And the first category is the macro scale category with a constitutive law, meaning that we describe the composite with its composite properties. So it's a phenomenological composite law. Yeah, we already talked. In principle, we could use an isotropic approach with a Mises plasticity, using MAT24 in that case, or star plastic, or MATA 103 for PEM crash. Or we go to a composite, meaning then we have elastic autotropic behavior. We could even define that in an anisotropic range, considering this orientation dependency, and couple this with a viscoplastic approach, which can consider also the orientation, and therefore it's quite common to use the Hill plasticity. You will find this Hill plasticity in all this in LS-DYNA, in PEM crash, and also Abacus. So that's a standard. In case of LS-DYNA, it would be MAT 157. So that's the formulation of this Hill plasticity. And if you think about it, it's like a Mises. It has just extra coefficients. These are called Langford coefficients or Hill coefficients, depending if it's 2D or 3D. This is the 3D approach. And as you see, that's some just scaling factors for the different directions, which meaning that it brings from a sphere to an ellipsoid, which is not the same as you see what we have in reality, but ellipsoid can describe this real scene stiffness behavior a little bit more than just a sphere. So what we need now for this approach in MAT 157 for this Hill material model. In that case, we need the anisotropic stiffness. So we need 21 coefficients describing this anisotropic stiffness. We need coefficients to describe the Hill plasticity. We need some load curves describing the plasticity and the failure. And it depends the stiffness, but also the other parameters are varying from the fiber orientation. So that's clear. Depending on what fiber orientation I will have in the real part, high orientated or average orientated in flow direction, this will influence our stiffness. And that's quite complicated to make a material card, because you just not need one material card. You would need several material cards for each fiber orientation. And that's too many possibilities to characterize. Okay, I would like to switch into the software again now, and just would like to explain you a little bit this MAT 157 now. So going back to that, what is happening? So I'm going back and now choosing LS-DYNA. And yeah, because I've chosen LS-DYNA, now I have several material models. Yeah, I want a material model with plasticity, and failure is free. So now I get this MAT 157. By the way, if you just say not selected here, then you get all implemented material models. Okay. And then we can say, yeah, we have a 2D or 3D approach in the deformation. In that case, I am choosing the 2D approach. Okay, so we use a 2D hill because we're using this with shell elements. So now what's happening now? For instance, we want to, yeah, let's start with this material model. Again, we have set up this before with this abacus properties, and you can see we have these engineering constants here, which was calculated with the micromechanic approach. But choosing now this different material model, we are getting new design properties here. You can remember that's the elasticity, this is composite stiffness. We are getting the Langford coefficients and so on. And we have then also to choose a function for the hardening, just a simple one, function for the strainer dependency. Okay, and yeah, that's quite fine. And yeah, what's happened in the micromechanics? So we started that's a short fiber reinforced material. We say that we have now polypropylene, for instance, so that we know polypropylene has around 900 density. That's some literature values. We know that we have 1500 Young's modulus, and we will have a yield stress around 15 and the strength around 20 for the failure. The failure, that's a rough values, a starting guess. And as you see, as I change the Young's modulus here from 1500 to 1400, automatically the values are calculated for this material model. And here, now I would say, for instance, I have glass fiber in it, not a fiber length of 200, it's short fiber. And here I want to have not 30% in it, just 20%, and the values are changing. And I can use this together with some tests and check it if this suggestion is good. What is quite nice in here is that we also automatically calculate in this library the Langford coefficients. So this parameter, what we have seen in this presentation. So I go back to this, say not hill 2D, I say 3D. Now I go back to this and say 25%. Then you see we're getting this FGH factor, which we have seen in before. Okay, so based with that information, then it's a good starting point to make material cards. Okay. So now go back to the presentation again. A different approach would be to use a microscale homogenization. I already mentioned the MAT for MicroMec. So in that case, we have the possibility to describe the matrix properties and the fiber properties, similar what we were using in our Valimat software's library. We can use this directly in the material model. And that is available in MAT 215. And for instance, that's the keyword, how it looks like. So first we have the card 1 with general options, with parameter. Card 2 and 3 are the element orientation. And card 4, you build up the composite. So you say the volume fraction, fiber length, fiber diameter, fiber orientation. The same thing what we have set up in our Valimat software is also directly implemented in LS-DYNA, and this fiber orientation here can be also overwritten by initial stress shell solid, so you can have an interface here in LS-DYNA. This card 5, you define the fiber material. Here are typical values, so if you would like to start, you find good starting parameters here to check how it works. Here for glass fiber or T400, these are the values which have to be used. So in case of the glass, it's isotropic material. In case of the transversal of the carbon fiber, it's transversal isotropic. As you see, different Young's modulus in fiber direction to transversal direction. And card 7 and 8 are the description for the matrix material, so defining the elasticity, defining the viscoplasticity. You can do this by some parameters like bilinear with Johnson-Cook, or you're quite free by defining the hardening curve in card 9, as you know it from MAT24, and defining the damage initiation curve like it looks like here, so how the failure looks like. And the same you can do for the damage evolution. So everything is available in the material card here. Quite interesting are the general options here. This general options offers you to switch on the failure on the matrix and the failure on the fiber. If you're just using 0 here, you just can post-process it. So in that case here and here, we see the fiber time, we see here the failure of the matrix. So the same step in this banding test, step 8 in the simulation, we see we are around 80% of the damage initiation, so quite close to the failure. At 1, it would fail. On the other side, if we are looking at the failure of the fiber itself, as we're using a micromechanical approach, we not know what stress is coming into fiber. We know we are about 10%, 30% of the fiber strength, so quite far away. So it's quite clear in that case, first the matrix will fail on the tension side, and the fiber will be then pulled out during that. Not the fiber will fail first. So that's some results what we directly see out of the simulation, what you don't will see in a composite build-up. So this failure criteria already mentioned can then be micromechanically motivated failure. As you know, the mean failure approach leads you that you can see what happens in the matrix and see what happens in the fiber. By dividing, you're getting from the solver the composite stresses in the step, the material model, you divide it into matrix and the fiber, and then you can decide, yeah, I would like to have a fiber failure, or I would like to have a failure on the matrix. And with this, I can easily set up a senseful failure model motivated on the physics, on the what is happening fiber side and matrix side. It's quite nice. Also to mention now is that the material models have different approaches, and therefore we have different advantages in taking this into account for the process simulation. So the process simulation, so if you make a mold filling simulation of a part, gives you a local fiber orientation information. So each element on your part will know I have this fiber orientation based off the injection molding of the filling. And if in case of this using the MAT215, the micromechanical approach, we can just map this information from one mesh to another mesh directly, because the material model itself understands the fiber orientation as input. In case of using a composite model, we have just take this fiber orientation and calculate first the composite properties and then map the composite material properties to the mesh. So in that case, you're mapping information of fiber orientation on it. In that case, you will, if you really want to locally consider the material properties of the fiber orientation, then you have to calculate on each integration point or each element before the material properties itself and then map this to the material model. So that's quite easy way, and that's quite expensive way in the beginning, and it's also quite complex to see if it's working fine. So there are tools needed like our FiberMap and MicroMec that you can do that. Okay, so now we have talking about material models, and next step would be how do we can get this material card out of tests. We already were talking a lot about some kind of characterization pyramids. Here's one approach we would suggest for this material class. So in that case, we typically would start with dynamic bending tests and static bending tests under different directions. So you can see it fails differently if you zero direction, it fails earlier. And if you look at the transversal direction, I go back here, you see we have first some wrinkles in here, and after this matrix is failing locally, then the whole composite is then failing. And you see this also in the signals. On the other side, if we do a puncture test, we then can see here quite good what Stefan also was showing. We have initial crack, and after this initial crack, crack is propagating, and yeah, that's something what we like to consider in our material modeling to be predictive in our simulation. So this slide I already showed in the beginning, the question, why not use tensile tests? And if we look at the fiber orientation over the thickness here, if we look on the fiber orientation over thickness here, we see that in flow direction in the skin, the fibers are orientated in flow direction because of the shear flow. In the core, the fibers are orientated transversal through the elongation flow. So if I do a tensile test, for instance here, we will do an average measurement over thickness. So we will have an average fiber orientation around this range, and we just can find out Young's modulus in this range of material properties. On the other side, if we conduct bending tests, we will always focus on the skin, and therefore if we do tests in longitudinal direction, we will get high values because the fibers are orientated in flow direction, the same as it orientated in the outer layer of the bending test. And if we do the test in transversal direction, we get values for the lower, for transversal properties. And so it's more easy to, if you make a material calibration and take the fiber orientation into consideration, you have to do some interpolation or extrapolation. It's always better to interpolate than to extrapolate, because you have to keep in mind, you will never be able to make a special sample for special fiber orientations. It's just a probability to find it. And so you just have the opportunity to calibrate the model and know around the fiber orientation in the model, and later on in the real application, that's an input from the process simulation or from an engineering a judgment. Here again, you see this fiber orientation over the thickness. It's a measurement of different regions. We have some plug here, demonstration plug. If you fill it in here and the flow is going there, then we have this blade region which an average orientation, and through this flow together we have high velocities and high shear stress in here. And if we look at the fiber orientation in the blade region, we have high orientated values in the skin, orientated transversal in the core, high values again in the skin. That depends if you're using a low viscosity material like PP or high viscosity material like a polyamide. This orientation, the shear stress has an influence, and the fiber length and the fiber content also, how this fiber orientation is distributed over the thickness. And through the geometry, as you see in this region, all fibers are orientated in flow direction, are mainly orientated in flow direction. And that shows you the big influence what can happen on the fiber orientation now. And if we do that and calibrate it on the bending tests, then we can find out that it's worked quite good for different orientations and also for the puncture test. And here you can see then the comparison of the test and the simulation now. Okay. Here again, a validation finally afterwards, after we have done the calibration. So the calibration was conducted on bending tests to calibrate the stiffness, the plasticity, and the failure. We validated this also in the puncture test. We will say later on how this works. And yeah, after this, the validation of these tests, again, the average test curve and the simulation curve of this ripped part. You can see the impact test and a quite good agreement. Okay, this can also be extended then to tensile tests if it is needed, if you are interested in, but from my experience, it's not needed for this material class, because you get every information what you like to have mainly out of these bending tests and puncture tests. But if you are interested in, you can also do these dynamic tests with impetus, and as Stefan already showed. So now it's time to make a coffee break, and after coffee break we would like to show you this, how it works in the software, and we will do this material calibration or material card generation live in the software. And yeah, if there are any questions, please give us your question in the Q&A. We could answer it then in the second part. So let's have 10 minutes coffee break, and we will see again 10 minutes after 10. Okay, have a nice break. Okay, let's start again after coffee break. I hope you enjoyed the coffee break. From my side, I did so. So I just got another question. In the simulation model of the WX-RIP, you have just shown the validation also included the Velimet software. How can it be used? That's the question. Yes, it can be directly used in our software. So we have it in it as a standard component. On the other side, it's also possible to use different components, and this will be shown tomorrow in the user-defined user-defined specimens. So if you're interested more on that, please come to our session tomorrow. Okay. So now we start with the next topic. We have discussed about, we were showing you about the material models which are available. What is the main difference between a composite approach and a micromechanical motivated approach like MAT 215? And now I would like to show you how you can generate a material card for this. And therefore, I think I like this example quite well because it really shows the advantages of using such approaches together with making material cards. So I already was showing you this this area where you see, okay, what is needed. We need some tests to make a material card, bending tests, bending and puncture tests for the failure, and finally validation. But you also have seen there are lots of inputs needed to make a material card, so it looks like quite complex. So on one side, we need from the fiber the mechanical properties, the fiber count, the aspect ratio, and the fiber orientation. So mechanical properties from the fiber are well known in the literature. And so you will find this, and it's also included in our software that you just can choose it. I've shown it to you with a drop down. Fiber content, aspect ratio is something you might know. If it's a real composite, you know about it, how much fiber is in it. If it's a short fiber reinforced material, you know a range on it, because the supplier says here, I deliver you at least 30 mass percent, so it can mean that 30 to 33% mass parts of the fiber are included for this material. And the fiber orientation itself, fiber aspect ratio or fiber length, is something what you know from experience, or you could even measure it by using some tests like ashing it. Fiber orientation itself, you can do it by doing some tests. For instance, making some micro-city measurements. On the other side, you can do also quite good engineering adjustment. From my point of view, I know roughly about what fiber orientation will be in a polypropylene or polyamide or a polypropylene terephthalate material in it, so that you also know from engineering side. The matrix, yeah, that's a little bit difficult because we have pseudo-mechanical properties. So on the beginning, the elastic behavior will be at that what we measure from a normal matrix. But as we are working with some averaging and homogenization, we can't use the real matrix properties directly because you have some local yielding at the fiber tips, for instance. So that's why I call this a pseudo-mechanical properties, and these pseudo-mechanical properties can be well found by reverse engineering. That's when we need Valimat to calibrate the hardening curve and the failure. And therefore we need tests. We can use bending tests under different directions. We can research this in uniaxial or biaxial direction with a puncture test, and we can look at static and dynamic behavior. So that's what needed is to make a material card like MAT 215. So here we have example. In this example, it's a polyamide, glass fiber reinforced 30%, and this E is for impact modified. So we have something in it we don't know. And what we have is we got some plugs provided from a research consortium, and we did some bending tests and under different moisture conditions, so dry, conditioned, and wet. And we also got provided these micro-CD measurements. So you know the fiber orientation over the thickness. That's the plate thickness. Yeah. And we conducted this test, and as you can see, we have a huge influence on the moisture content. So this is the bending test in zero direction, in injection molding direction. Depending if it's dry, it's quite brittle, stiff and brittle. If it's wet, it doesn't fail. So as you see, we're getting more and more weaker and ductile with more moisture content. And the same we will see in the puncture test, dry, conditioned, and wet. Wet is meaning having it in a water bath. Conditioned means at room condition after several weeks. You can do this also with some conditioning procedure, and dry as molded. So we know that's the influence of the matrix based on the moisture content. And yeah, how we can now generate a material card for that. And I will do this now in the software directly to explain it to you what is happening. Okay. So we now see the whole software. And in this software, we have a database with different tests, as I mentioned, with different moisture content. And in that case, I have tests for different orientations. You see, I have a bending test. I have a bending test here for static, for different orientations and velocities. The same I have in a dynamic way. And if I would look on one model, for instance, I could look in here and look at the measurement results. So what we have currently for this, for instance, so I plotted the measurement results here. So you see we have static at 0 direction, dynamic at 0 direction. We have static at transversal direction. We have dynamic at transversal direction, and we have the static at 30 degree and dynamic at 30 degree. This is the bending tests what we have, so we can directly measure see the influence of the anisotropy. And if we would like to model that, we could start with a simple approach. For instance, we start quite simply, and for that, I would first start with a MAT22 card. So we're switching now to this model. I was showing you this before. So we have now included this test for different directions. I just interested in the Young's modulus. This is always the first step. So therefore, I do a optimization. I do the settings for the averaging here to 70% of the maximum force of this test curve. So I can set up this, and yeah. Maximum force here. And if I now go to the composite setup, and yeah, we could keep in mind that we have said that this material model has around 30% fiber content. We know it's a short fiber. And if we go back to the presentation, now we will see that around this level, 80%, around this level, 80%, we have the fiber orientation. So that's then an input in our model, 80% in the first direction. We know also the second direction, the third direction. That's what we can give in it. And then we get values for the Young's modulus and so on. And if we just simulate that, so we also can add then the matrix. So that's something what we set up, the Young's modulus of the matrix, the density of the matrix. And if we then simulate this in our software, so we can now look at the simulation result, we will see that this model automatically suits quite well to the different direction in the beginning of the dynamic behavior. So if we would like to see how is the influence here, we could also just go here and say, yeah, I would like to change the value to 0.5 and 0.49, for instance. So now we would say it's average orientated, and I again say average orientated, and now again I can say, yeah, I create a model. I just start the LS-DYNA job and see what is happening. So this is a quite quick run, you see. So that's how you just set up and check what is happening. So I get directly the result. And you see clearly, I've set up averaged orientation, and then I get the same stiffness as this 30-degree cut it out sample, because this is an immediate result. Other possibilities, yeah, I would like to see what happens if every fiber is orientated in the maximum direction. Let's do this again. We recalculate it just and see what happened. And so you just adjust your parameters quite fast, and within some minutes, you get a suitable setup for the main micromechanical data. So what, just to see, set up what is the right value, for the fiber content, the fiber length, and the fiber orientation, because that will not change. That's something what is fixed at the material model. Changing is after the deformation, the plasticity, for instance, or the failure. That's nothing what will change during the simulation. And as you see here, if you use a high orientated, we're clearly to this high orientated range. So when we then are fine with this first approach of this orientation, the next step would be then to use this fiber orientation and go to the next step, to the plasticity. And so before I go forward, I would like to show you the difference in the material models first. So I did the same for this MAT22 with the integrated micromechanics in our ValeMat. So there's a composite deformation. I did the same for the MAT 157. You see that's the same properties here. And I get the same results mainly. I can also compare it directly. So get the same result. And you see, we set up these micromechanic options. These design variables are calculated with the micromechanics. And in the background here, each of these design variable the starting value is coming from the MicroMec calculation. That's this flag what is showing you that. And yeah, so that's quite easy implementation here. And you see, that's what I was telling you before. This is how a composite setup is. Now let's have the same look at the elastic behavior for MAT 215. And in 215, I don't have any micromechanics in here because this is a micromechanic model. And in the model itself, the design variable are not the composite variable. In that case, I define the matrix properties, the 2500 here, and I define the fiber content, the fiber length, and the fiber orientation here. And let's have a look on the result on the elastic behavior, the difference between the 215 and 157 in the elastic behavior. And let's compare it again. And you see again, we are quite close from the result between these two approaches for the elastic and Tomanians here. Okay, so I wanted to show you how to get the initial properties for the composite build-up. This is the step 1, set up the composite. The next step is getting the matrix property. I already told you about the pseudo matrix behavior. So in that case, we try to use the material. We try to use those tests which are influenced mostly of the matrix, and that will be the test in transversal direction. And we know about this that in transversal direction we have a static and a dynamic test. And the static and dynamic test here, we can then calibrate our matrix properties. So again, I go back to the software and will show you this step. Okay, so I have also prepared it a little bit. One moment, please. Oh, it's up here. Okay. So what we have now here. So this model is prepared like we have two load cases in it. So the load case, the static one. The static one and the dynamic one. For the hardening optimization, we take 70% of the maximum curve. And in the material behavior, it's the same properties in the micromechanics. So in that case, we have the same Young's modulus, the same properties, the same mass percentage, the same orientation in here, what we found out in the from the first step for the setup. And now we do it like in the original optimization, we have our design variables. So the micromechanics are all coming from our calculations, like here the composite materials. And now we have to fit the hardening function, and therefore we can do this for this MAT 157 too, same like for MAT 215. We just have to fit the viscoplasticity values, the VB factor, and the hardening function. And if we look then, I already did this optimization. So I will open LS-up to show you what is happened in the background. Okay, so we have the setup here. In the background, we have a look at the history, and we see we had these design variables. We have the yield stress, which were running into these bounds, but yeah, we started at 30. For this example, I set it the bounds quite close. The hardening, it ran to the lower bound, and the VB factor. So in that case, I would rerun it, perhaps because I ran into bounds, so that I make it more possible to find a better optimum, perhaps. But you see, after 3 steps, we finally came then to result, and this result looks like that. So we just fitted the plasticity by using reverse engineering, by changing these properties here by LS-opt, and finally got a good agreement in the static and dynamic test over 90-degree orientation. So quite straightforward. And after that we have done this, the next step is then we validate this model for all orientations and directions. That's not the best fit. We could improve here, but as you see, we could do the same orientation and plasticity for 3 meters per second, and the same we can do for 215. But in that case, we have the values as design variables of the matrix in here. And if we just compare these two models, again, we will find quite similar results. Yeah. So now go back to the presentation again. Let's look if there are any new questions. No, there are not. Okay, so let's go back to presentation mode. Okay, I've shown you that to get these parameters, and you can also see with this information we did this for the dry, conditioned, and wet material, and we found out this hardening curves. This is for the strain rate of 0.001 for 100 per second for the dry one. Blue is the same for the conditioned one, and green the same for the wet one. That's the matrix properties. And as you see, I didn't change the setup of the composite. I just changed the matrix properties. Then for each calibration, I did this for get these values under 90-degree. Next step would be then validation of the dynamic bending tests and get the failure strengths. And after getting these failure strengths and setting up these failure strengths in a ductile, in a damage initiation model, I will also validate this on a puncture test. And after doing that, I have this nice slide. I really like that. You see, we took the same composite built up in all these models, and just by changing the matrix properties, we can describe the behavior of the material by having different matrix property for dry and conditions for all orientations, for static and dynamic, and also for the puncture test, and also for failure, which I think is quite good thing to show what opportunities you have. And the big advantage is that you could, even if you're using MAT 215 in that case, if something is changing in a real application, for instance, you have some conditioning in between, you just can take an average value of your matrix properties and have a look what will happen. So it's quite straightforward to do that. Okay, now coming to the topic, what else? So I would like to show you a picture of our injection mold, which we're typically using for making this material characterization. And I would like to show you two parts, some parts. So here we have the plate, where we typically cut out samples. Then we have our sample plate, where we have injection molded tensile samples and injection molded bending samples, which are highly orientated, and where we have this double X rib, which can be used for this component test. And we have also one plate for investigations of melt and weld lines through the flow here. Through the flow here, we're getting here a melt line, and here we get the weld line. And that's quite interesting to research. And we can then consider this fiber orientation and map it by fiber mapping. And here you see this injection molding simulation of these two parts of the block, where we did the calibration of our material model, and another the block with this melt and weld lines. And here you can see the fiber orientation over thickness. You see that the red value is around 80%. In the center, it's not as we measure. So in the center, we have around this level here. It doesn't flip really. So we have a little difference in it. And here we can then map this fiber orientation from the injection molding to the bending test and use this local fiber orientation information with our calibrated material model. And yeah, we also coming to a good agreement between the real test and the simulation. But also, to be honest, we had to scale the hardening curves around 20%, because our calibration didn't consider that the fiber orientation we are getting from the injection molding is not 100% perfect. So it doesn't mean that we should not use these tools, but it means it's not perfect at the moment. And this fiber orientation, what we get from the injection molding simulation, has always a little bit different. It always is not so much orientated as we have in reality. And that we have to consider. But if we scale then our hardening curves, then we also can describe the real material behavior, as well in the bending test as well as in the puncture test. We did the same then for this melt line. So you see here these different properties here. We had to scale the failure strains around 30% in this region of the melt line. And using the same value here for the weld line, you also can describe this behavior quite well. So that's quite interesting that this simple approaches, this engineering judgments here work quite fine to describe what is happening. So now let's have a look on the case study itself. So you can remember we have this sleeve, and we did the simulation with the isotropic behavior. First, I have shown it to you. And here we have the injection molding. We see the fiber orientation, which is coming out of this Moldex simulation. And then you see the fiber orientation, how we mapped it and with fiber map. So we have this local distribution in our simulation model. Remember, that's the test. Remember, that's the isotropic result. And that's the anisotropic result with MAT 157 or 250. In both cases, you will get a better result. There's slightly difference between these two models. So if we look at the force displacement curves here now of the test that was done for the conditioned one, we see the test, that's the red solid line, and we see that our simulation mainly described what is happening in the test with the MAT 215. We have this slight difference because these simulations were conducted with the mentioned calibration process, we didn't consider this 20%, which I have shown you from the mapping procedure. So if we would scale this also here, we will lead to this final result. So a big improvement compared to the MAT24 result. And the same if we do it for the dry one, and if we do this for the conditioned one, we see that this is quite good agreement between the simulation in principle to the test. Again, this 20% are the big difference. Okay, now I would like to hand over to my colleague, Harish. Harish will give you also a quick view on the composite now. And yeah, Harish, it's your turn.
Okay, thank you, Peter, for the really nice introduction to MicroMec and FiberMap and the different modeling possibilities with short fiber reinforced thermoplastics. I would like to give a small, quick introduction into long fiber reinforced plastic materials. So the possibilities that we have with composite materials with all our test and software solutions. So composite. So as all of you know, there are different kinds of composites depending on how you lay them up. So you have your unidirectional, you have your multidirectional, that is fibers oriented in different directions. So as you can see here, these are all the typical test setups that we offer with the impetus system. For the unidirectional, we have the tension tests, and then we have also the bending and the puncture tests as validations. So what are the available LS-DYNA material models for composite materials? Sorry. So as Peter introduced all these models before, we have MAT22, which is like an orthotropic, elastic orthotropic material model, which does not consider plasticity or any strain rate dependencies. Failure can be set. And then we have MAT54 and 55, which are a bit more complex versions of the MAT22. And then we have MAT58 and MAT158. MAT158 here is an interesting model because it's a model that you can consider time effects with. So you can model viscoelasticity or strain rate dependent material or composite material models. And then we have MAT 261 and 262, which are more complex continuum damage based models with an option to define nonlinear shear behavior. They are basically the setup in the same manner, but MAT 262 differs in in the underlying continuum mechanics model. So composites, how do you set them up? You set them up in almost exactly the same manner as Peter showed you before, using the MicroMec approach. Then you have your MAT composite damage, the MAT22 material model, and then you have your material card case, the damage failure case, and then you can, in MicroMec, choose endless fiber reinforced plastics instead of the short fiber reinforced plastics that Peter showed before. Then you can define your matrix and your fiber values, and with also your strength properties. So on the left, you see here, like we have overview of all the material models that are available, which are accessible when you select not isotropic elastic in the elasticity option. So you have all the models that I just introduced before. We have also the MAT 4A MicroMec, the MAT 215, which Peter gave a really nice introduction on earlier. Okay, so again, we have our micromechanical approach where we define the matrix properties, the filler, the fiber properties, and then basically information on the orientation and the strength. As Peter also showed, how the design variables are accessed directly from MicroMec. So they just passed on directly from MicroMec. You see this option in under design variables for MMec. Okay, so this is an example. So we built up a stacked shell here, as you can see on the right, for the validation. But first, the orientation dependency with the 3-point bending. So we have the 0 degree in red and 45 degree in blue. This has been done with a MAT58 material model. So as you can see here, we have very good agreement with the test results with the material card. Then we also have the strain rate dependency here and a multi-layer setup to basically validate the material card as shown here. And as you see here, the stepped failure is actually quite well represented. Ending words with composites, we have a case study here, which is basically a front hood of a commercial car. So the front hood was a honeycomb structure. So we have a skin layer and then a comb layer and then a core layer. And then using all these tools at our disposal, Valimat, Impetus, and MicroMec, what we were able to do is we were able to define a composite layer with layup with an anisotropic material behavior. We characterized the skin and the core materials separately so that we get a good, so that we get the material cards for the whole layup. And then we did and then the customer did a comparison of how the material card performance is in comparison to the real test. So this is a head impact. So as you can see here, we have a hood and then we have an impactor hitting the hood. So the picture here shows you the resulting accelerations over time. And as it's very clear here from the curve that the test and the simulation go really well together. So this was a broad overview over the last 2 weeks. So we have dealt with thermoplastics, fiber reinforced plastics, and now carbon composites, so carbon materials. We have shown you the capabilities of basically all our solutions and how they can be applied for you to get efficient material cards for different material classes. So as a summary from today, so different models are needed for characterizing different materials. So for example, we have composite material models and we have the SFRT, LFRT, which differ in your fiber content. So Peter gave you an introduction of basically 2 main approaches. One is the macro scale composite behavior with and then the micro scale behavior that distinguish between the fiber and the matrix behavior. So to summarize, what are the differences? When you use a micro scale model, you are very flexible in defining your layups in your what you want to get out from the composite layup. But the obvious disadvantage is these models are computationally a little more expensive. The macro-based models, on the other hand, are computationally less expensive and if done right, can give you comparable results to the micro-scale models. That is, again, based upon experience. So just some organizational things. The presentations will be uploaded as well as the recorded stream. We are working on them intensively. We will get them up and running within the next 1 or 2 days. For the people in the audience who want to have a trial license for Valimat, my colleague Mr. Schober posted a link in the Q&A section in the Q&A chat section with the forms link. So if you have any further questions, please feel free to ask now, or please contact us at valimat.support@4a.at. And what we would really also like from your side is to give us your personal feedback on the different sessions. So thank you very much for your attention.